Welcome to organolysis. So welcome to another video of the name reaction series. Now in this particular video we are going to discuss the important name reactions as well as the organometallic reactions, and they are basically called the cross coupling reactions. So from today onwards we are only discuss about the cross coupling reactions. There are lots of cross coupling reaction and there are some name cross coupling reaction that's are very much important. So we are starting with the Heck coupling reaction. Now for this cross coupling reaction you have to know some basic things that are needed to this to do this Heck coupling reaction or any kind of cross coupling reactions. Now we are starting with the Heck coupling reaction. Now this for this Heck coupling you have to know that this type of coupling reactions is basically to form a carbon-carbon bond. So we are try to produce a carbon-carbon bond formation by using this Heck coupling or any kind of cross coupling reaction. So this is the prime motive of this reaction. So don't waste time and let's start the video. So for the basic things to do this Heck coupling is that you have an alkyl group or any kind of R1 X or any X is your any kind of leaving group, and along with this you have to put a alkene over here, and using this you have to use this palladium 0 catalyst along with this ligand, base, solvent and heat. You are getting this kind of bond, this kind of structure, or like alkylated or arylated product. So depending upon the R you are getting different kinds of product. But in the year of 1970, so in the year of 1970 Richard F. Heck and the Mizoroki, they are first independently discovered the benzyl or styrene types of compound reacted with the olefinic compound in the normal elevated temperature. So they are getting and by using this palladium catalyst and along with the amine kind of base, that is basically they are basically use the amine base. So by using this they are getting an olefin which is basically called the palladium catalyst reaction, that is basically called the Heck coupling reactions, right? So these are a very much important tool to form the carbon-carbon bond. So first we have to see the R1 group. So R1 is basically your aryl, benzyl or vinyl or any kind of alkyl group. But in case of alkyl group you must know this concept that in case of alkyl group there must not present any kind of beta hydrogen. So why this with no beta hydrogen is present in the alkyl compound, I will be discussing on later. And this R2 and R3 and R4 are basically the alkyl, aryl or any kind of alkenyl group, and the X group are basically any kind of leaving group that are basically the Cl, Br, iodine, OTF, that is a triplet group, OTS, that is a tessylate group, or N2 plus can be used. And you can see over here the palladium catalyst is used, palladium 0 catalyst is needed for this reaction. But along with this you have to put the ligand. So ligands are basically triphenyl phosphine or trialkyl phosphine. So you know that this is any kind of PPH3 or PR3 kind of group, and the base is needed. Now this base is basically the 2 degree or 3 degree amine or any kind of NaOH, that is sodium acetate or bicarbonate kinds of base. So this is all about the basic concepts and which things are needed to do these reactions. Now in this X, that is your leaving group, there are some order to determine the rate of the reactions. I will do it on later. So let us first discuss the mechanism of these reactions. Now the mechanism for this Heck coupling is not fully understood, and the exact mechanistic pathway can be varied in different kinds of reaction or changing upon the substrate. So basic requirements for this Heck coupling reaction is you have to know some basic organometallic reaction. I think you all know that what are the basic organometallic reactions. That is a kind of oxidative addition, migratory insertion and reductive elimination. These three parts are very much important. So first part is important, that is the oxidative addition, then the migratory insertion, and third is the reductive elimination. Another point is also be noted to the in this organometallic reaction is the beta hydride elimination. This is also very much important tool for this to do this mechanism of this reaction. So let us start the first mechanism. So we know that palladium catalyst, palladium 0 is not such stable, so we are basically this we are getting this palladium type of compound in this way, that is your palladium 2 or palladium 4. So we have to reduce this palladium 2 to palladium 0, and then we will move on to the mechanism. So first we are starting with the any kind of palladium, if is it palladium 0 or maybe palladium 2. If it is palladium 2, then you have to this is your pre-catalyst. So palladium 2 is basically generated in this way, that is PDOSE whole 2. So this kind of substrate, okay, you have to reduce this into the palladium 0, and then we will do the overall reactions. So when we are using the palladium 0, so this is our 14 electron system. So we are starting with the palladium 0. So this is our pre-catalyst. We have to do in this way, that is your palladium in 0 state and attach with the ligand. So this is your 14 electron species. So this is our 14 electron species. Now we are starting with the, now why I am doing this mechanism in this bracketed arrow, because of these are the catalytic pathway. So we are getting the same compound at the end of this reaction. So we are starting with this Rx. So this is your oxidative addition step. So this is our oxidative addition step. So in case of oxidative addition, we know the oxidation state of this palladium will increase by unit by 2. So we are getting this palladium 0 to palladium 2, and along with this is the oxidative addition that we are getting from here along with this one. So from here we are getting the 14 electron to the 16 electron species. So this is the palladium 2 now. Now this is your 16 electron species. Now this is the step that when this type of alkyl will insert in this compound. Now alkene is basically, we are writing this one, that is R4 and R3, R2, and this is your hydrogen. Now this step is basically called the migratory insertion. So this step is your migratory insertion, right? So this is a migratory insertion. Now from here we are getting that there is a two types of possibility, that this palladium will either insert in this position or in this position. So to know this concept, you have to know some basic knowledge about the transition metal complex. So in case of transition metals, they all are less electronegative comparative to the carbon. So carbon is more electronegative. So this palladium will always attach to the more substituted end, or where the electron is greater in amount. So in this case you can see over here that is these two R groups are present. So this carbon is basically highly substituted. So this is basically stereospecific and regiospecific as well. So this palladium will directly attack on this carbon, and this overall group R group will attack on this position. So this is your migratory insertion step. So this migratory insertion step, what we can get over here, that this is your R2 and these two are in same side. So we can write in this way, that is these two are in the same plane. Now this R1 will attack over here, and this bond will attack over here. So we can write this palladium in this way, palladium Ln, and along with this this X. Okay, so we can write in this way, and here we have the hydrogen, and these two hydrogen are in the same side. So we are getting this one. Now this is your carbon-carbon single bond. Now this carbon-carbon single bond can rotate. So why this single carbon bond rotation takes place, you can see in the next step. So this is your carbon-carbon bond rotation. So this is your CC bond rotation. So in this bond rotation we are getting, this is your R2, this is your R3, these two are in the same position. Now to do this single carbon single bond rotation is basically the we already written over here that the beta hydride elimination is needed. Now this beta hydride elimination is always happening in the syn fashion, so this is basically called the syn beta hydride elimination. So that's why we have to write this hydrogen and this palladium complex in the same plane. So that is why we are rotating this carbon single bond. And now that is why the CC bond rotation is takes place in these reactions. So we are getting this hydrogen over here and along with this palladium Ln, and this is your X, right? So this is all about the complex, and this palladium is in 2 oxidation state. Now from here we are getting this one, and this here you have the R2 and here you have the R4. Now from this we can see over here that this is your alpha position, that is palladium is attached, and this is your beta position. So now the syn beta hydride elimination is takes place. Now from here this type of elimination is takes place, and you can see over here this R2 R3 in the same side and R2 and R4 in the same side. So from here we are getting the alkene which is our desired product, that is these two are this is R1 basically. So this is your R1, so this is your R2, this is R3 and R4 in the same side. So we are getting this is our this is R1 actually. This is our major product, and from here we can remove this one, that is this is your X. Now we are removing this palladium hydrogen complex, so this palladium hydride will remove from the system, and this is in 2 oxidation state along with this Ln, the overall ligand. Now from here to here we can generate this compound, that is your 14 electron complex, and that is basically called the reductive elimination. Then this step is called the reductive elimination step. So from here we can generate this removal of this HX. Now you know this reductive elimination is always takes place in cis fashion, so this HX will leave from the system, will leave from the system, and you are getting the ultimate compound, and that is we are going to start with this from this reaction. So that is your 14 electron complex. So this is also 16, all are 16 electron complex, and from the 16 electron complex we are getting the 14 electron complex. So this overall electron transfer is very much important, and that's why this reaction is quite important and quite necessary for the carbon-carbon bond formation. I hope this mechanism is clear to you. If you have any problem regarding this mechanism or any kinds of of the Heck coupling reaction, you can directly ask me in the comment section, right? So let's move on to the key points that you should remember, and that's are very much important for this Heck coupling reactions. So first key point is that it is an important method, as I already told, that the important method to carbon-carbon bond formation reaction. Next point of this reaction is the reaction can tolerate the wide range of functional groups. That's basically A star, ether, carboxylic acid, phenol, nitriles, or any kinds of dienes. Next, third point of this reaction is the more substituted olefins are undergo in less comparatively slower in the Heck reaction. But in case of unsymmetrical alkene, that is a terminal olefin, they are predominantly undergo at the less substituted olefin. As I told you earlier, that the carbon is comparatively more electronegative from the palladium any kind of transition metal complexes. So that is why this palladium is always attached to the more substituted end, not the less substituted end. So that is why this palladium is always attached in the more substituted, where the electron density is higher comparative to other centers. So this is what it is, the regioselectivity. And next point is the nature of the X. Now this is quite important concept, that is you should know, if you have a compound that contains iodine and bromine, so iodine will react faster comparative to bromine, then the OTF and the Cl is comparatively less reactive. So that is why Cl is not basically used in some cases. Basically they are using this iodine, iodide or bromide types of complexes. Fifth point is the stereospecific reactions. Now this stereospecific reaction, as I told you earlier, that is a beta hydride elimination process, is basically syn stereochemistry. So when you have this palladium and hydrogen, it has to be in same plane, so then this elimination will takes place. So this is quite stereospecific. Another point is to be noted, that the regiochemistry. Now when you have this chemistry type of compound, you can see over here, you can break this bond in this way because this is electron withdrawing group. So you are getting this negative charge over here, and you are getting this. So when you are using any kind of Heck reaction, so palladium will attach over here, or any kind of alkyl or aryl, that is I can write over here as R. So it can attack in this position, but the palladium will attack in this position. So we are getting the final compound as a major product. This R will attack in this position. Similarly, if we have this compound, the major ratio will be changed comparatively. So this is your 100% is to 1. So this is 0, and this is your 99 is to 1. So this any kind of R group can directly attack over here, and in this position you are getting an carbon-carbon bond functionalization. And finally you are getting this. If you have this kind of compound, you are getting the amount of the 79 or 21 kinds of ratio. So this is our regioselectivity of these reactions. Next point is the examples. Now examples are very much important. So you can see over here you have given the palladium acetate. So from this you have given this iodobenzene and this kind of substrate. So you are getting this product. Now how can you get the product? So let us do the mechanism first. So the hydrogen this halide with changes with the palladium center. So this we can write this whole OAC2 group in the Ln form, and this is your iodine. So this is now in 2 oxidation state from 0 to 2. So you are getting this pH palladium complex. Now then you have this group, so we can write in this way. So this will coordinate with this one. So from here we can write, so this, now you know that here you have the electron density is comparatively higher, so palladium directly attack in this position. So you are getting this palladium over here, and this is your CO2Me, and here you have the 2 hydrogens. Now this hydrogen can be written in this way, that is up above the plane or below the plane. Now this hydrogen is, you can write this palladium complex in this way. Now you can see over here this we can write this hydrogen are in the, you have to rotate this bond, basically not in this way, actually you have to write in this way. So this hydrogen and palladium will remove from the system, so that we can get this kind of major product. So this is our final and major product from this reaction. Next we have another compound, that we have this one, and you can see over here this alkene is present in the same molecule and iodine is present in this way. So this is your leaving group, and you have the same reagent, that is PDOAC whole 2. So I am not doing the overall mechanism, I am written over the direct product. You can see over here this palladium, this iodine exchange with the palladium, and it will attack over here, and this is called the intramolecular Heck reaction. So this is an example of intramolecular Heck reaction, right? So this is our intramolecular Heck reaction. So you can see this this is our pH. So you can write this pH over here, and this is your CO2Me. Sorry, not here. This is our pH. Here you have the hydrogen. You can see over here 1, 2, 3, 4, 5 and 6. You are getting this 6-membered ring over here. This is your hydrogen, and the palladium is present in this way. So this palladium is in below the plane, and you have the hydrogen in above the plane over here. So there is no scene elimination is being takes place. So that is why this hydrogen go here, and this palladium will remove from the system. And finally the product that you get from this reaction is this one, that is the alkene is being transformed from here to here, and the final product that you get is this one, right? So this is our final product from this reaction. So this is our major product from this reaction. Now let's see another compound that we have. Similarly, this iodine bromine will exchange with the palladium, and finally the product that you get is this one, CO2Me, like this, right? So this is our major product. So this is our major product. Now next comes that this one. Now this we can see over here, that is you have the Br and iodide, and I already told you that the iodine has a greater reactivity comparative to iodine in the Higgs coupling reactions. So this iodine will first reacted with this complex of this compound, and you are getting this kind of product, right? Now let's see this one. Now this is a previous year question as well. Now this question came in December 2016. The question says that you have given the substrate and the palladium 5% PDOAC whole 2 like this. So this is let's see how to do this question. Now you know that first the iodine will exchange with, now we can write this palladium, iodine and Ln complex in 2 oxidation state, and here you have the NH2. Now you can see over here these two are, this is triple bond C and the CH2OH and Me3Si. Now which one is more substituted? Now you can see over easily that this SiMe3 is comparatively larger, so this side is comparatively more substituted from this CH2OH. So this palladium complex directly attack to the more substituted end, so that you can get this kind of product. That is, so this we can write CH2OH and SiMe3. So this will attack over here, and this bond, this CH2 will bond directly attack in this position. So finally the product that you get from here is this one, CH2OH. Now this is your double bond, now this is your SiMe3, and this is your palladium overall Ln complexes, and here you have the NH2. Now you can see over here, this is your alpha position, this is your beta position, but there is no beta hydrogen. So that is why this NH2 will directly attack over here, and this will go like this. So the final from here we can get, and this is your CH2OH. Here this negative charge directly takes a proton from the from this one, so that you can get SiMe3 and the PD-Lni complex. Now you have the beta hydrogen over here. Now the beta hydrogen can leave from the system in this way, and the final product that you get is this one. This is your CH2OH SiMe3. Now this question is quite important and very much interesting question is this one. Let's see some previous year questions. The question came in, first question came in NET June 2017. Question says that you have given a substrate PDOAC whole 2. You have to predict A and B with correct stereochemistry. So first thing, you have to change this palladium. So this will attack with the palladium 2 and overall Ln. It will change its oxidation state 0 to 2, so that you can get this type of intermediate, and this will attach with this. This you can see over here the electron rich center, that is, this will directly attack over here. You can get a 5-membered ring, and this palladium will attack in this position. So finally the product that you get from here is this one. This is a double bond. Now the bond formation is being always takes place in the same stereochemistry. So if this methyl group is in the above the plane, so this group has to be approached in the same plane, that is in below the plane. So if it is both are approached to the below the plane, so this hydrogen will go in above the plane, and finally you can see over here this hydrogen is above the plane. So you can see this palladium is in below the plane. So to remove the beta hydrogen in same fashion, so you have to remove, that is in this position. So you are getting the final product. So this is your A, and the final product that you are getting is this one, hydrogen methyl methyl. So this is your final product with correct stereochemistry. So that is why you are not going to get a alkene in this position. You are getting the final alkene in this position because this hydrogen is not seen to each other. So scene elimination is not being takes place in this position to get the alkene in this position, right? So this is our final product from this reaction. Next comes out that the question NET December 2018. The question says that you have a alkene, that is this double bond, and you are getting this overall big substrate, and the reagents are quite similar. So you can see over here that this lone pair can push its electron in this way, so that you can get the negative charge in this position, which is quite stable, and here you are getting this electron deficient center. So you have the negative charge over here, so this negative charge directly attack with the palladium iodine complex. So this is now palladium iodine complex, So this palladium will directly attack in this position. So finally that product that you get from here is OMe. So you can see this is your palladium LNI complex, and the whole R group will directly attack in this position. So right, so you can see this hydrogen over here. Now these two are seen to each other, so it can remove in this way. So finally the product that you get from here. Now why this base is needed? So base is needed basically to remove this beta hydride elimination, to facile this beta hydride elimination, right? So this is what you get from here. So this is the final product from this section. Let's see how easy the question and how simple the question was. Next question comes, that is the GATE 2016. Question says that if you have this substrate and PHBr, so this PHBr is your major substrate that will combine to form this along with this C double bond C, and you are getting the CC coupling product. And finally that you have given this PDP PH3 whole 4 and HOKOC, that is a base. So similarly the product is basically, you can easily predict what will be the product. You can see over here this oxygen, so this can push a electron in this way. So this here you are getting the negative charge. So basically this negative charge is basically the electron rich center, so it will combine with the palladium bromide complexes, so that you are getting palladium bromide and Ln complexes with this one. And finally you are getting this CH3 and this pH over here. So now you have the hydrogen over here that are cis to each other, so there is no beta hydrogen, so this hydrogen will remove from in this way. So finally the product that you get is pH and methyl. So this is our major product from this reaction. See how easy the question, and you can do it in 1 second just. Let's see another question. The last question of this video is the GATE 2019. The question said that the long series, you can see that this substrate is given in the rotated form, so you didn't identify what will be the product and how to do this reaction. So to do this you have to rotate first a bond, so to comparatively easier to do this reaction. So first you have to rotate that bond, so the question will be easier to you. Now this bond goes like this way. Now you can identify what will be the product for this reaction. Now you can see over here palladium is given, so this PDI Ln is overall complexes, and this is your comparatively more electronegative side, so this will attack in this this R group is attached over here, and this palladium is attached in this position. So finally that you are getting this one, and along with this cyanide, and you have the palladium over here. So there is no beta hydrogen, so you have to remove this hydride over here. So finally that you get product this one. So you are getting this final product CN like this way, and this is your CN, right? And what will be the next step? So this is your P. You have to identify the Q as well. So the first you have given the LiLH4. So LiLH4 is basically to reduce this cyanide group. So if you are using AlH4, lithium aluminum hydride, it will reduce cyanide to corresponding CH2NH2, right? So this is our product that we get. So, and along with this that we are getting TS. So this is our CH2 NH2. This here is a double bond. Now you have given the Ac2O. So you know that lone pair is comparatively more reactive, so it will attack with this Ac2O. Ac2O is basically acetic anhydride, COCH3. This negative charge directly attack over here. One can go back and it will leave from the system in this way. So finally that we are getting the Q is this one. CH2 NHCO, so CH3. This is our major product from this reaction, and this is Q. So that's it for all this video. This is our first carbon-carbon bond forming reaction and basic organometallics reaction. So this is our first cross coupling reaction as well, right? So I think I have covered all those topics related to this coupling reaction. I also covered the overall examples, and that maybe come in future examinations. And if you like this video, keep sharing with your friends, and I hope this video is very much helpful for you. If you have any doubt, let me know in the comment section, and don't forget to subscribe this channel. So that's it for this video, and thank you so much for watching.